Applications of CRO. So, a cathode ray oscilloscope is a versatile instrument in electronic industry. So, modern oscilloscope is the most useful device that makes it possible to trace out the trouble quickly. Some important applications are the CRO can be used to measure the current, voltage, maybe AC or DC. Can use the CRO to measure the power, the frequency, the phase difference between two waveforms, the time period, the depth of modulation of a modulated waveform. We can measure the pulse parameters, the different parameters like rise time, fall time, and the pulse width to trace the signals of radio frequency, intermediate frequency, and audio frequency in radios and TVs, to examine the waveforms, to see a composite synchronized TV signal, antenna radiation pattern, etc. So these are the various applications of a CRO. So as I already told you, you can measure the time of a waveform, time period of a waveform, you can measure the voltage, the current, the phase, the depth of modulation. You can observe the different types of waveforms, the composite video signal of a TV, and you can also see the radiation pattern of an antenna. So now let us see how the time is measured for time period of a waveform is measured. So here 5 milliseconds per division is selected on the time per division switch. 2 cycles of a sinusoidal waveform displayed. 1 cycle is completed in 5 divisions. So the time period is calculated as, for 1 cycle, I told you, it needed 5 divisions. You can see on the display screen. So 1 cycle needs 5 divisions. So 1 division is 5 milliseconds. So 5 milliseconds into 5 divisions, 25 milliseconds is the time period of the waveform. So the time period and frequency of periodic signals are easily measured with an oscilloscope. So the waveform must be displayed such that a complete cycle is displayed on the CRT screen. So accuracy is generally improved if a signal cycle displayed fills as much of the horizontal distance across the screen as possible. So the signal to be measured must be adjusted in such a way that it must be comfortable for us to make the calculations. So the waveform is displayed on the screen as shown. So the time per division is noted down from the front panel controls, and the number of horizontal divisions for one complete cycle is noted down from the display. Then the period of the waveform can be calculated as T equals to time per division into the number of divisions. This gives you the time period. So the current measurement. So CRO is basically voltage indicating device. If you want to measure the current using a CRO, the current to be measured is passed through a resistor. The voltage across the resistor is applied to the CRO and the voltage is measured. This measured voltage divided by the unknown resistance gives the value of the unknown current. So the CRO can also be used to measure the unknown current. Next. to measure the unknown voltage. You connect the signal voltage to be measured to one of the channels, either channel 1 or channel 2, and adjust the volts per division switch in such a way that you observe a waveform so that the calculations are easy to be made. Supposing now the volts per division control is the portion of 2 volts per division, then from positive peak to negative peak we have 6 divisions. So the amplitude of this signal can be calculated as number of volts per division into number of vertical divisions from peak to peak of one cycle. So in this waveform, we have selected 2 volts per division on the front panel control of the CRO, and for one cycle from peak to peak, there are 6 divisions. So the amplitude is calculated as 2 volts into 6 divisions is equal to 12 volts peak to peak. This is how the voltage measurement is made. So the most direct voltage measurement made with the help of a CRO is peak to peak value. So the RMS value of the voltage can then be easily calculated from peak to peak value. So to measure the voltage from the CRT display, we must observe the setting of the volts per division control and the peak to peak deflection of the beam, that is the number of vertical divisions of the waveform. Then the peak to peak voltage is given as volts per division into number of vertical divisions. In this case, it is 2 volts into 6 division. It is 12 volts peak to peak. This is how we measure the voltage or the amplitude of a waveform. Now, I told you we can measure the DC voltage, we can measure the AC voltage, we can measure the currents, we can measure the phase of a sine wave, we can measure the depth of modulation, different pulse parameters also. So here, let us see how to measure the DC voltage. So here, while measuring the DC voltage, first you have a front panel control switch, AC, DC and ground. Put that switch in the position of the ground. You will observe a trace or reference line. You adjust that to be in the center of the screen. Next, so as I told you, select the reference line, adjust the trace so that it is in the middle of the display using horizontal position control switch. Now you apply a DC voltage. You connect a DC voltage to the CRO. Put the switch in DC position as I told you and apply the DC signal to the CRO. As soon as you apply the DC voltage, the reference line which was in the center of the screen display has moved up by 2 divisions. Supposing my volts per division control is in 5 volts per division and the trace lot or the trace line is shifted up by 2 divisions from reference line, then the voltage is calculated, the DC voltage is calculated as volts per division into number of divisions it has shifted. So here the volts per division is in the position of 5 volts per division and the reference line has shifted by 2 divisions. So 5 volts per division into 2 divisions is equal to 10 volts. Now the voltage which is measured is nothing but the DC voltage of 10 volts. Now let us see how we measure the negative DC voltage. So you can see on this display the position of the volts per division is in 5 volts per division position. Now the reference line is shifted down by 2 divisions. So the DC voltage is calculated as 5 volts per division into, it has shifted down, so you can take it as minus 2 divisions. It is nothing but minus 10 volts. So this is how we calculate the negative DC voltage. So if the reference line move, as soon as you connect the DC voltage to the CRO to be measured, if the reference line moves up, it is a positive DC voltage. If the reference line moves down, it is a negative DC voltage. So we have seen how to measure the DC voltage. Now let us see how to measure the AC voltage. The voltage to be measured, you connect the AC signal to one of the channels of the CRO, either channel 1 or channel 2. You slowly adjust the time per division control and volts per division control so that the waveform is displayed clearly so that you can take the readings easily or comfortably. In this example, supposing the volts per division control is in 2 volts per division. Now, I want to measure the amplitude of this AC voltage. So, from the positive peak to the negative peak, there are 6 divisions. So, the amplitude can be calculated as 2 volts per division into 6 divisions. That is volts per division into number of vertical divisions on the CRO screen. So 2 volts per division into 6 divisions vertically gives you 12 volts peak to peak. Next is the measurement of time interval and frequency. So again, you apply the signal whose time interval and frequency are to be calculated. Adjust the time per division and volts per division controls so that the waveform is displayed. Now, after the waveform is displayed, for one complete cycle, you check how many horizontal divisions are there. So, for one complete cycle in this display, it is 5 divisions. Now, you see the time per division switch is in 5 milliseconds per division. So now the time period of this waveform is calculated as time per division into number of horizontal divisions. So in this example, 5 milliseconds per division into 5 divisions is 25 milliseconds. This is the time interval or the time period of the waveform. This is how we calculate when the waveform is displayed for one complete cycle. You check how many horizontal divisions are there. In this example, there are 5 divisions. Next, you check in which position is time per division control. It is, in this example, it is in 5 milliseconds. So the time period is calculated as time per division into number of divisions. That is 5 milliseconds into 5 divisions. It is nothing but 25 milliseconds. Once we know the time period, you can calculate the frequency as already we know frequency is nothing but f equals to 1 by time period. In our example, we calculated the time period to be 25 milliseconds. So, the frequency is 1 by 25 milliseconds. It is nothing by 40 hertz. So, now we have seen if you apply an AC signal to measure the amplitude, you have to check the volts per division control in which position it is. So volts per division control into number of vertical divisions for one complete cycle from peak to peak. To calculate the time period of frequency for one complete cycle, you check the time per division control into number of horizontal divisions for one complete cycle, which gives you the time period. Time per division into number of horizontal divisions gives you the time period. So, to calculate the frequency, 1 by time period is nothing but the frequency of the unknown signal. Next, to calculate the DC voltage or to measure the DC voltage of a signal applied, put the switch in DC position. First you put the switch in ground position, adjust the reference line to be in the center. Next you put the switch in DC position, apply the DC voltage to be measured. The reference line shifts either up or down. If the line shifts up, then it is a positive DC voltage. If the reference line shifts down, it is a negative DC voltage. There also number of divisions shifted we have to check. So volts per division into number of divisions it has shifted gives you the DC voltage applied. While making the AC voltage measurements, we have to put the switch in AC. First you put the switch in DC, ground, adjust the reference line to be in the center, then you put the switch in AC, then you apply the signal to be measured to any one of the channels. Here you can see the different controls. The gain control, that is nothing but to measure the amplitude. The Y shift, you can move the waveform. Y shift is nothing but vertically. Next is the time base. You can adjust the waveform time base. Next is the X shift. You can move the signal horizontally. These are the different controls. You can vary the different controls like the amplitude, frequency, X shift, Y shift, time base, gain. Different controls you can vary and you can see the changes in the display. So this we have already seen how to measure the peak voltage. It is we have taken the number of divisions as 3 divisions into 1 millivolts per division. Then you get 3 millivolts as the amplitude of the wave peak voltage. This is how we measure the time period of the sine waveform, and from there 1 over t gives you the frequency of the signal. So here in our example, the time period is can be calculated as number of horizontal divisions is 4 and the time per division control is in 1 milliseconds. So it is 4 milliseconds. Frequency is nothing but 1 by time period, which is nothing but 1 by 0.004 seconds. So the frequency is 250 hertz. So you can vary the input signal by changing CRO controls and you can measure the input signal. Next, coming to the phase measurement. So phase shift describes the difference in timing between two similar signals. So here in this waveform labeled current is said to be 90 degrees out of phase with the waveform labeled voltage. Voltage waveform has started earlier than the current waveform. Since the waves reach similar points in their cycles exactly one-fourth of a cycle apart, that is 360 by 4, it is 90 degrees. So here the phase difference between the voltage waveform and the current waveform is 90 degrees. Here you can see the waveform. One waveform is colored red, one waveform is blue in color. The difference between the two waveforms starting point is one division. So if you check the time per division control, supposing it is in 5 milliseconds per division, then the two sinusoidal waveforms of same time period 25 milliseconds are displayed. The distance between 2 points which are in same phase is displayed as one division. So the phase difference is 5 milliseconds into one division is 5 milliseconds. So here in terms of angle, the phase difference is 5 milliseconds into 360 degrees by 25 milliseconds, which is nothing but 72 degrees. So this is the phase difference of the two signals. So using Lissajous figures also, we can measure the phase difference. So here the CRO can be used to determine the phase difference between two AC signals of same frequency, which using Lissajous figures. So if you want to measure the phase difference using Lissajous figures, you should keep the CRO in XY mode. So as oscilloscope can be used to determine the phase relationship between two voltages of same frequency, two signals are applied simultaneously to an oscilloscope without internal sweep. So you have to keep the CR in XY mode. One signal is given to the horizontal channel and the other signal is given to the vertical channel. So the resulting pattern is called as a Lissajous figure and it shows the phase difference between two signals. The Lissajous patterns are useful to find out the phase difference between two sine waves. They are useful to find the unknown frequency of the sine wave. The patterns showing the phase relationship between two sine waves of the same frequency are shown. The different Lissajous patterns will indicate the different phase differences between two waveforms. If the phase difference between two waveforms is 0 degrees, then you observe a crossed line as shown in the figure. If the phase difference between two sine waves is 45 degrees, an ellipse. If the phase difference between the two waveforms is 90 degrees, we observe a circular display or the circular Lissajous pattern. Similarly for 180 degrees, 270 degrees and 360 degrees, also with different frequency ratios, also the different patterns can be observed. So using Lissajous patterns also, we can measure the phase difference between two signals. And next, depth of modulation. A modulated signal, we know it's nothing but carrier wave is the carrier wave amplitude is changed in accordance with the audio signal or a video signal, or we call it as a base signal. So here when you apply a modulated signal to a CRO, You will observe the waveform as shown in this figure. You will be you will be having two parameters here. Vmax, that is a maximum peak to peak voltage, and Vmin, that is the minimum peak to peak voltage in the waveform. So the modulation index can be calculated as measure the Vmax, measure the Vmin. Vmax minus Vmin by Vmax plus Vmin gives you the modulation index. And if I need the percentage of modulation index, it is given as M equals to Vmax minus Vmin by Vmax plus Vmin into 100. So these are the few applications of a CRO. So to sum up, we can use a CRO to measure the current, to measure AC and DC voltages. You can measure the power, the frequency of a waveform, the phase difference between two signals. You can measure the time period. You can measure the depth of modulation of a modulated waveform. You can measure the different parameters of a pulse. Also, you can observe a composite video signal and also the antenna radiation pattern. These are the different applications of a CRO. To measure the DC voltage, put the switch in DC position and apply the voltage to be measured to one of the channels. So the reference line gets shifted up or below the center line. So if it moves up, it is a positive DC voltage. If it moves down, it is a negative DC voltage. If you want to measure AC signal amplitude and frequency, put the switch in AC position, apply the AC signal. If you want to measure the amplitude, you check the volts per division control. So volts per division control into number of vertical divisions, the waveform is gives you the amplitude of the AC signal from peak to peak. And if you want to measure the time period, check out the time per division control, in which position it is, into number of horizontal divisions for one complete cycle. That gives you the time period of the waveform. 1 over time period is nothing but frequency of the sine wave. Next, if you want to measure the phase difference between two sine waves, then you have to see the difference between the two waves, the time period or the time difference between the waveforms of reaching the same point. So that gives you the phase difference of the sinusoidal waveforms. You can measure the phase difference using Lissajous patterns. And the last one, you can measure the depth of modulation of a waveform by calculating Vmax, by calculating Vmin. So Vmax minus Vmin by Vmax plus Vmin gives you the depth of modulation. Okay, thank you.